Hey everyone, and welcome. So today, we're going to crack open the academic playbook to really understand the mind of an engineer. We're going to piece together a blueprint, but not for a building. No, for a way of thinking that literally constructs our modern world.
That's a huge question, right? We see the end results all around us, the skyscrapers, our smartphones, the power grids. But what's actually going on in the mind of the person who designs it all? To figure that out, let's look at three, seemingly totally random pieces of a puzzle.
Okay, so here's our first piece. This is straight out of a thermodynamics assignment. You've got energy values, something about a cyclic process, it's dense, it's specific, and it's all about the hard physical laws of heat and work. Yeah, a bit intimidating, right? Okay, just hold that thought.
Now, piece number 2, this comes from a probability and statistics course. We've just jumped to a whole different universe, right? We're not talking about heat and energy anymore. This is abstract stuff, dealing with data, with uncertainty, with making educated guesses. How on earth does this connect to thermodynamics? And for our grand finale, piece number 3, this totally cryptic line from a digital electronics class. So this isn't about physical stuff, it's not about chance. It's a language of pure logic, of ones and zeros, of absolute, unbreakable rules. So let's recap. We've got heat, we've got chance, and we've got logic. What is the common thread here?
Well, the connection is everything. These aren't just random, painful subjects that students have to grind through. No, they're the core components, the absolute building blocks for a disciplined, creative, problem-solving mind. This is the engineer's blueprint.
All right, so here's how we're going to break this down. First, we'll decode what this blueprint is all about. Then we'll dive into each of our 3 core components: uncertainty, energy, and computation. And finally, we'll see how it all snaps together. Let's get into it. So if you really want to understand how engineers create all the technology we rely on every single day, we've got to get inside their heads and see how they're taught to view the world in the first place. It's a way of thinking that's deliberately built piece by piece through their education.
Okay, so our first building block, and you could argue it's the foundation for everything else, is statistics. Think about it. Before you can build anything that works reliably in a world that's, kind of random and unpredictable, you have to learn to speak the language of uncertainty. You have to know how to manage it.
And this syllabus, it lays out that journey perfectly. Just look at the progression here. Students kick things off in week 1 with the basics, just describing data. But fast forward to week 8, and suddenly they're wielding these powerful tools like Bayes' theorem to update what they believe based on new evidence. It's literally a step-by-step guide to taming randomness. And this is where all that theory hits the pavement. Hypothesis testing. It's basically the formal, rigorous process an engineer uses to answer those make-or-break questions with real confidence. Questions like, is this new alloy strong enough for the bridge? Or, is our factory actually making parts that are the right size? It's all about getting rid of, I think so, and replacing it with, I can prove it with 99% confidence. All right, so we've been in this abstract world of data. Now, let's do a hard pivot into the real physical world. This is where engineers take these unbreakable laws of physics and use them to design things that move, that heat up, cool down, and generate power. Welcome to the world of thermodynamics.
Just look at this problem. It's a high-stakes calculation. You've got mass flow, you've got velocity, you've got this thing called enthalpy, which is basically just the total energy in the system. Getting this wrong isn't just a bad grade on a test. In the real world, a miscalculation here could mean a power plant literally fails, catastrophically. This is where theory gets very, very real.
And this is a perfect illustration of the engineering method in action. When you're faced with a problem that looks this gnarly, you don't panic, you follow a process. First, define your system. Ignore everything except the turbine. Second, apply the fundamental laws of physics that you know are true, like energy can't be created or destroyed. And third, you solve for what you need, the power output. It's this beautiful, methodical way of turning total chaos into something you can actually solve. Okay, so we've got a way to handle uncertainty, and we've got a way to control energy. But how do we build the brains of the operation? That brings us to our third pillar, the logic of computation, which, believe it or not, all starts with silicon, which is really just super purified sand. Wild, right? So to build a computer, you need to be the master of electricity. You need to control its flow. Now, as you see here, conductors, like metals, just let it flow freely. Insulators, like rubber, block it completely. But the real magic ingredient, that's the semiconductor, like silicon. Its special property is that you can control its conductivity. That ability to control it, that's the key to literally all modern electronics.
So the very first, most basic thing you can build with these semiconductors is something called a p-n junction. You probably know it as a diode. The easiest way to think about it is like a one-way street for electricity, or maybe a turnstile. Current can go one way, but it can't go back the other. And that simple little trick, directing the traffic, that's the first step on this huge ladder of computational complexity.
Okay, so once you know how to build these little one-way streets, you can start combining them into something way more powerful, a logic gate. And trust me, this is a huge leap. A logic gate isn't just directing traffic anymore. It's making a decision. A simple one, sure, but it's a decision like, hey, is input A and input B both on? And the best part is, these decisions follow super strict, totally predictable rules. We lay them out in what's called a truth table. So for this AND gate, you can see right here, the output is only one, or on, in one single scenario, when input A is on and input B is on. And by stringing together millions or even billions of these simple little decision makers, engineers can build circuits that do all the mind-blowingly complex stuff your computer is doing right this second.
And this right here is the language they use to design all of that. It's called Boolean algebra. That little expression you see there, it's not just some abstract math. It's a literal blueprint for wiring those gates together. It means the output Y is on if A and B are on, or if C and D are on. This is the language that built our entire digital world.
Okay, so we've looked at three completely different fields: statistics, thermodynamics, and digital logic. Now it's time to put all the pieces together and see what the final blueprint of the engineering mind actually looks like.
Because this right here is what it all builds to. See, an engineer isn't just a specialist in one thing. They're an integrator. They use statistics to deal with risk, thermodynamics to harness the physical world, and digital logic to create intelligence. But the real superpower? It's systems thinking. That ability to weave all of these different ways of thinking together to solve a single complex problem. That's what creates everything from your car to your phone.
This is the blueprint that built the world we live in right now. But, as we start facing these huge new challenges, things like AI, quantum computing, synthetic biology, it really makes you wonder, what new courses are going to get added to this list? What are the new, essential building blocks for the next generation of engineers? And that's the question I'll leave you with. Thanks so much for digging into this with me.